Good. All right. So I'll just grab one of these pens. Let's see. There was one of the problems I just wanted to talk about. Do you mind real quick? Thank you. From last time. I think things went pretty good on that first one. It was, and I made a lot of comments. Even if you didn't lose any points, you might want to check through, because I did definitely point out a few things. But on that second problem, the activity 313 with the second derivative, we had a graph that looks like this. And honestly, if anybody lost a point, it would probably just right at this one. And it was only like, look here, this is something that you want to keep an eye out for, not -1, believe it or not. And then this was the double prime. So thank you. So the question was, where do we have any inflection points? And so inflection points, you definitely need the first derivative equal to 0 at an inflection, second derivative equal to 0. But it's not an inflection point unless you cross the axis. So this has to change sign. And, so I'll put a little x critical there, or x sub inflection, f at xi, f double prime, changes sign. So what it means is that, now I'm also remembering something else I want to mention. You want to talk about the change in concavity. So concavity is, am I concave up? And I don't think I think only a couple people actually answered that one the way I wanted. Concave up or concave down? And concave up is this kind of scooping upward. Your tangent slope is increasing. Concave down is your tangent slope is decreasing. And that can look all sorts of different ways. But it's where you change from this to this. So an inflection point is concave down to concave up. So that's an inflection. Or concave down, concave up to concave down. So all inflection points kind of look like one of these two scenarios here with that change in concavity. And so that's what I was looking for here. This guy is just chilling out. You've got negative concavity on this side, and then it kind of gets a little flat, but then it becomes concave down on the other side. So that's not an inflection point. And then also on there, I asked you to do a sign chart and talk about concavity. And everybody did the sign chart great. So this is G double prime. Everybody got that. You've got a 0 here and a 0 here. But when I say address the concavity, your second derivative, everybody kind of got this. G double prime is positive here, G double prime is negative here, and G double prime is negative here. So this is concave up. Be more explicit about that. This is concave down, and then concave up. Concave down again. I didn't take off any points for that. I just like noted it in most everybody's. Is there any questions on the stuff you just got back? Good, cool. We're gonna keep doing those. I think those are good, having those harder problems that we work on together. I have a problem, and I kind of wanted to warm up with today. So let's say I've got this function, f of x equals 2 plus 3 over 1 plus x plus 1 quantity squared. For the sake of the chain rule, or just to keep you from using the quotient rule, I'm gonna write it like this too. Maybe it's a little better way if we're gonna differentiate it, and we are gonna differentiate it. So I guess step one is, could you please find any critical values here? Find the critical values. Warm up problem. Gotta take a derivative. This time you definitely gotta take a derivative. just to let you know what's coming up so you can keep working, is mark the CVs on a number line and test the sign of f prime in each region. So we're thinking first derivative test here. Yeah, not yours, huh?
No.
After you do take that derivative, you'll probably want to rewrite it as a fraction, just to make it easier on your brain. Yeah, why wouldn't, so we would want to think about the bottom, do we have to worry about it? How come? I agree, but I want to know why. You didn't pop your hand up, did you? Okay, okay. Yep. How are we feeling about this derivative? Looking okay? Pretty cool on that? Okay, good, good. And I'll put a couple other questions that we're going to talk about up there in case you are working fast. That is. Why is the bottom not a problem? I agree with you.
your top looks great, so definitely -1. So now we gotta ask ourselves, can the bottom be 0? So let's write out the bottom real quick. Just write out what the bottom is. Cool. So now we got 1 plus something squared. Can that thing ever be negative? How come? I agree. Yeah. So this is always, and if you're at -1, it's 0. But what is the least this bottom could be? What is that always greater than or equal to? That 1 plus that there. Yes, yes. Well, this is always greater than or equal to 0 here. But what about the whole thing? What's the least value you can get out? Yeah. So there's no critical. No, there aren't any. Because the bottom can't be 0, we don't have to worry about a problem with that. Does that make sense? So you got it right. Oh, yeah, you got it. Yeah, that's it. Long story short, you got it. You got it. But it has nothing to do with the bottom. Oh, that's the key. Let's talk real quick, just to give you some sanity checks. Critical values where the top equals 0, and that's going to be at x equals -1, or where the bottom is 0. But the bottom can't be 0. What is the least the bottom can be? Yeah, what is the least the bottom can be here? 1.
Or I solved it. Yeah.
Oh, okay, cool. Do we all see that? Because this thing here, this is greater than or equal to 0 because it's a thing that's squared. So you've got 1 plus a non-negative thing. The bottom is always bigger than or equal to 1. So I can't get a critical value out of that. You can keep trying, but it's not in the real numbers. So we only get x equals -1. Everybody cool with that? Yeah, cool, good. And then we make our sign charts. We only have one thing to worry about. That's awesome. To the left of so when x is, let's go to the right, it's low-hanging fruit. When x is 0, I'm gonna test that over here. The top is negative, the bottom is positive, so f prime is negative here. And when x is like, say, -2, I've got -2 plus 1, that's -1 times -6, that's positive. So over here, f prime is positive. That means I'm increasing and then decreasing. So I have a what at x equals -1? A local min. And then we gotta get in there, and we gotta ask ourselves, is there any way it could be higher, right? So we definitely have a local minimum at x equals -1. And one of the things I'd like you to get used to is explaining why by the first derivative test. I started writing stuff on folks' papers, adding in extra verbiage that I'd like to see. But just like always give a little reason. Don't just say, this is that. We've got things we can cite. So it's just like citing evidence in your, your compositions. Cool. So I think we kind of have all that. What about question 3? It says this thing is always bigger than 2. Why is that? So it's saying this function here, this quantity, 2 plus 3 over 1 plus x plus 1 squared is always greater than 2. How come? Yeah.
Because if you manage to make the right part of the function 0.
This thing here?
Yeah.
Yeah.
The right part, all of it, the fraction.
Mm-hmm.
It's always gonna add to that plus 2.
Can I make this side 0, make this piece 0?
Not normally. You could plug in an imaginary number, but I don't think
we can,
No.
right? Because we need a number on top to make it 0. We need a 0 on top. So you're right, you're thinking the right way. So this thing here, the most this thing could be is when the denominator is as small as possible.
What is the smallest that this can be? 1 is equals 1, and that's where? Where does the smallest value of this occur? What x value? And x equals -1, right at our critical value. So this is the smallest at 1. That means this is the biggest it can be at x equals -1. And then as this thing becomes non-zero, the denominator gets bigger. And the whole ratio becomes smaller. So what we see, something like this, at -1, we've got our high point, and then we're kind of decreasing, but we actually can't ever get to 0, and we can't ever get to 2. Do you see how this thing is never equal to 0? So the best I can do is get closer to an output of 2. So there's this horizontal asymptote right there. It lives above the line y equals 2. Cool. And then let's look at this. So I've kind of hinted at it. What are these limits?
2.
Yes, they're 2. Yes. Because as x gets bigger, the denominator gets bigger, and this thing goes to 0 as x gets big. And since you square here, same thing happens in the plus or minus versions of infinity. So the graph looks like this. Kind of looks like a bell curve, if you know what that means. You know, in statistics, the normal distribution curve. Probably had some bastard teacher who did that to you at some point. This is actually an absolute max, right? That's actually an absolute maximum. Is there a minimum? Is there a minimum of any sort, absolute, otherwise? Yeah, why not, Eddie? I agree. Maybe you weren't shaking your head and I called on you anyway. Maybe that was drinking, head shaking, Sam.
Because since you have a horizontal asymptote, you can never get to that value. You will infinitely get closer to it and never actually reach it.
100%. So there's no minimum value we can reach. We can only get closer to 2. Did you guys do a lot of drinking this weekend or something? You folks seems pretty spaced out in here. Cool. So f of x is always greater than 2, and there is no minimum. That's a big M. It's a lot of M's, humps in the M. So when can we actually know that there will be a minimum? This problem's kind of hard. What if I change the problem? So I'm going to keep the same function. All the work we did is still totally valid. And I say find the absolute max and min, but I change what x can be. So imagine how much better this problem would be if we didn't have this, oh, I just trickle away forever. I just trickle away forever. What if I said to you, hey, let's find the absolute max between x equals 0 and x equals 4. And I cut down the range. Can I do that problem? Yeah. Here's the absolute max, here's the absolute min. So if I restrict my inputs to a closed interval, I can always do this. Find absolute on 0 to 4. So we're going to come back and do this, but I'm going to show you, you're going to be so happy with this because you've done the hard part. And we still need this step, but I'm going to explain to you what we need to do to solve this whole sucker. So there's a simple result that this all lives upon, hinges upon. We have this thing called the extreme value theorem. You could call it the EVT when you cite it. And we want to practice citing things, right? Like, oh, I'm using the EVT, so blah, blah, blah. Extreme value theorem says if f is a continuous function on a closed interval, a to b, then F attains an absolute max and an absolute min on that interval. You need continuity, and you need this thing to be finite and closed at the ends, because you can see what happens when it's not finite and it's not closed at the ends. You can just trickle away and never reach a minimum. So it attains an absolute max and min on AB. And here's the plan, how to find these. This is the easiest damn plan in all of Calc 1. How to find, exclamation point. I'm so freaking stoked about it. Step 1 is find all critical values of F. And here we're assuming it's differential. Well, no, it might not be differentiable. Find all the critical values of F that live in the interval you're interested in. So you're gonna find all the critical values, and then you're gonna look, okay, I found a critical value over here, -1, but my interval over here, my AB, is 1 to 4. That doesn't live in that interval, so I don't have to worry about it. If these critical values aren't inside there, forget about them. Awesome. Step 2, find the following. F, this is the original function. Find out how high it is at the left. Find how high it is at the right, and evaluate F at every CV from step 1. Essentially, you're making a list here. You're making a list of outputs. Step 3 is from this list, the largest output from step 2 is the global max, is our absolute max. And the least value from this list right here in step 2, the least output from step 2 is our absolute min. And then you want to report. So step 4 would be summarize, and let's start practicing getting better at summarizing our answers, adding a little verbosity. So step 4 is summarize. There's like a lot of M's. Summarize by the extreme value theorem. We know there is an absolute max of, and then you'll put the F here at x equals blah, and then an absolute min of, and the of is what the output is at that location, at x equals blah, blah, blah. So let's do this problem right here, finish it up. Let me give you a second. Finish writing that whole plan down. If you can't read that, like there's clearly not that many M's in summarize, I guess. I don't even know if that's an M. We come to our problem. Step 1, find the CVs, but I'm going to write here, but -1 is not in 0, 4, so disregard. We still have to find it to make sure and to prove to our reader that we know what's up, we know what's happening. So step 2 is so sweet. Step 2 is find f of 0. The left endpoint. What's f of 0?
3.5.
Yeah, 2 plus, yes, 2 plus 3/2, right? So 3.5, yep. Cool. We already know from the way this looks, that is the max value, because remember how it's sloped downward? So we know it's only downhill from there, but we'll just go ahead and do this. F4 is, well, hell, I don't know. Has anybody actually simplified that?
2 and 3/26.
2 and 3/26. I love it. Cool. Whatever the hell that is. We're done. Step 3. By the, well, step 3 is kind of like look for the largest and smallest, so let's just skip that. It's pretty obvious who's biggest, who's smallest here, so obvi. Step 4 is summarize. So there is a global or absolute, you can use global or absolute interchangeably, I clearly do, max of 3.5 at x equals 0 and a global min of 2 and 3/26 at x equals 4. Done. Any questions? Or we're gonna work some together. And I was kind of thinking on Wednesday, I've been liking this where we just work problems together in class. I like bring problems in. Does that work for you all? It sure beats web work. That's what I'm thinking. And we can make things harder. Like, you know, those problems I bring in, those are challenging. In a different way than web work, where you're like, feeling like you want to take a sleeping pill. Like that. All right, so let's practice. Let's practice. And we've got some applications coming up with this stuff. Maybe that's where we want to go. Let's see, what did I plan on next? Well, let's do a few to warm up, and then we'll do some awesome applications. I'm very excited about these applications, by the way, so let's practice. Determine the absolute, I'm going to toss in a word here to save writing for all of us, extrema. That encompasses maxes and mins. Extreme points, extrema. Extrema. I don't know, not a Latin. Anybody here taking Latin? Nobody is? That's good. That's good. I always have lots of math students taking Latin. I'm like, what do you do with that? Oh, we don't have a Latin program anymore. I gotta let go. That sucks. That's why you're not taking Latin. Determine the absolute extrema. H of x is x e to the negative x on 0, 3. Let's practice our plan. Step 1, find your critical values that live in 0, 3. Sometimes they'll sync up with the endpoints. That's okay. Sometimes not. Kind of hoping not here. factor probably, that first derivative, just for your brain's sake. Good mental hygiene with math, is to make things a little factored. Is there any questions on that derivative? Do you want me to walk through it? We good? Really common theme is that e to anything cannot be zero, right? You can't get zeros from e to something. That was kind of what I wanted to reiterate by doing this problem. What are the critical values here? 1, just 1. So x equals 1 is the only CV. Is that in our interval? It is. Cool. So we will consider it in our lists in step 2. You know, feel free to use a calculator when you're evaluating these, because you're probably like, well, does he really want me to know what e cubed is? Not really. You can do this without it, but it'll make you happier to have your calculator out for sure. So let's keep you happy. My gut tells me the 1 over e is the biggest. Is that checking out? Calculator agrees with me, good. And one good thing to keep in mind is that e is, you know, it's around 2.7, it's 3-ish. You can always use that for just ad hoc estimates. I don't know why we had a step 3 that says look at that list. I'm not going to do stuff. We're looking at the list. We're picking the biggest, largest. So absolute max of absolute min of, what is my min? What's the least number here? 0. That worked out. X equals 0. Oops, sorry, and I think this number here, you could kind of think if e's 3, this is approximately like 1 over e squared, which is approximately, you know, a 9th or so. Just like rough estimates, thinking of e as a 3. Kind of put it through. Is there any questions or anything on that one? Cool. Do a trig one? Who said that? Oh, that's a good good idea, definitely. Nobody will fess up to it. So let's do this one. P of t is the sine of t plus cosine of t. And our interval, oh, I can't let you get by without thinking about pi. Remember those graphs we did at the beginning? The sine and cosine graphs, they might play in here, who knows? We'll see. Look for just a, like, you get, are we cool with this? I hope that was like, just like, okay, I got that part. Cosine of t minus sine of t is your derivative. When you set that thing equal to 0, and these are never undefined, so we don't have to worry about that. Realize that that is really the same as this. And so you're looking in this interval for where these two functions are identical on output. Look at the graphs. Draw the graphs out. Or do this however you want. There's a lot of ways to solve this. I want to give you some time to freak out on. Not in the bad way. Freak out like, I'm a freak, I like trig. That's the kind of freaks we like in here. We like all kinds of freaks. Freaks make the world better. So, let's see. Just for other ways of thinking, you could also find where tangent is 1. That might be easier, whatever you like, but there's only one special triangle where the tangent is 1. Remember, tangent is opposite over adjacent. Think of a triangle where the tangent is 1. Thinking about a 45-degree angle where those two are the same. So pi over 4 is going to be your critical value. And that that is definitely in there, right? So we're good, we're gonna have to think about that. And then we have to test the endpoints, and these charts should make that easy, these graphs I put up. Oh, duh, no, that is wrong. That is garbage. Good, good, good. Absolute max of root 2 at the pi over 4. Absolute min of -1 at the left endpoint. Any troubles, questions, things we should talk about, you'd like to talk about? Okie doke. I got one that I want to ask you a slightly more general question about. We're not going to do this one, but what if I gave you this problem? What if someone gave you this problem? We've got q of x equals x squared over x minus 4 on 3, 7. Can I use this process? Can I use the extreme value thing? Why are you shaking your head, Sam? I agree.
Because 4 is in the, when x equals 4, bottom of 0 is in 5.
So you're not continuous. There's an asymptote here. Yes, exactly. So this function has a vertical asymptote at x equals 4, which is inside that interval, so you can't use this process. What would the max be? Infinity, and then minus infinity, or something like that. So because Q is not continuous on 3, 7, we can't use this method. We can't apply the EVT. If I change this to this, suddenly we would have to do the work, but we're not going to do that. Does that sound all right? Yeah, sounds good to me too. Let's build some stuff. This is some fun. We're gonna do some building of things. And first thing we're gonna build is build a box. Build a box. So we've got a sheet of paper. We're gonna build it out of paper. We've got a piece of paper that is 8.5 by 11 inches. Norm, the piece of the paper you got with you, the handouts, all the shit, that's 8.5 by 11. May not look like it, but it is. So what I wanna do, and I'll show you the basic, does anybody have scissors? Oh, I'll show you, you're awesome, yes. Love it. I'm gonna show you what we're gonna do, because I never thought about actually just doing this to show everybody what's going on. Exactly, yeah, fist bump. Thank you, MacGyver. Thank you. This is good. I got a lot of weird shit in my bag, but it's none of it's useful. So I appreciate someone who does. So what we're gonna do to make a box out of this piece of paper is I'm gonna, first off, I wanna just fold some things here so that I can aim my cuts a little bit better. I'm gonna cut a square out of each of the corners. You can see it's almost forming a box already, right? Like if I just kind of like left it like here, it kind of would hold some, I don't know, hold some things loosely but crappily, not well. It's kind of gonna spill out. So what I'm gonna do is cut a, thanks Asha's scissors. I'm gonna cut a square out of each corner, and they're gonna all be the same size, hopefully. So I cut that out, I cut that out, that guy, and I will remove that dangler. Oh, no. Asha gave me scissors and I can't even use them, right? Jeez. Okay, so what we're gonna do is cut a little square out of each corner, all the same size. So this distance is this distance, is that distance. The length of all these little cuts is the same. And then I'm gonna fold it up like this. And we're gonna make a little box. See the basic idea? So now our question is, what is the biggest volume I can hold in this box? Because I could have made those cuts really tiny. Let's draw some pictures. So for this box, if I made a super tiny little cut here, 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 and here, and I put this box together, it's gonna look like a shallow pan, right? So, and notice that this little cut, if I make a square that's X by X, that's actually the height of the box when I'm done. And then there's a little, get out of your way, Jasmine, just a second there. So if I do that, I get a super shallow, look like a tray or something. Or if I do a really big cut, what's the biggest cut I could actually make? If I want square, just cut out of the corners. Like physically real. Yeah, like 4 probably, right? Like 4.25 if I wanted to have nothing left. So like the most I could cut across here would be 4.25 inches. But I would probably want less than that. So let's say I cut just 4 inches, like Addie said. And then I've got some weird little thing like that. Cut a 4 inches out of here like that. And this box is pretty terribly drawn. So those are 4-inch squares, believe it or not. And then when I fold this thing all up, what it's gonna look like is a really weird box that has a thin side. So this little side is that right there. And then it kind of looks like the tray on its side, and this is open at the top. So the volume is going to change depending on how big this square is. My goal, our goal, is to find the optimal cut to maximize what this tray holds. So we're gonna set up an equation, and we're gonna model the situation pretty much like we started here. We're gonna say that I've got an 8.5 by 11 sheet, and I'm gonna cut a square of side length X out of each corner. So we're making that cut, right? And then that's gonna be like that. It's gonna be like that. X and X. So I'm gonna make those cuts, and then I'm gonna fold my box up, and let's get a picture so we can see what that's gonna look like in general. And I'm gonna fold along that line, that line, that line, and that line. And I get myself a box that looks, this is gonna be a much better box than my previous boxes. And that is an open top box. Looks about like that. how tall is the box? X. X is the height of the box. This cut width here, when you bring those guys together, you get a box of height X. X. Let me stop. Does that make sense? Everybody see how we're building this? Okay. Cool, cool, cool. How wide is this? So this is the width of the box. What is that W here in terms of X?
8.5 minus 2.
It was the original length minus an X minus an X. You see, we had 8.5, we removed X and X. So this width here is 8.5 minus 2X. What is the length? Somebody besides Addie help me with that one. Same person that called for trig is answering now. What's this one?
11
Thank you. 11.
inches.
Yes, and then after I take out the bits, you're right. How do I adjust it then? I'll show you.
2x.
Yes, thank you. Thank you, ma'am. Thank you. So we got that. How do you find the volume of a box?
Multiply the 3.
Multiply the 3 dimensions, length times width times height. So the volume, in terms of X, is gonna be length times width times height. And so that's gonna be, it doesn't matter which or which here. We're just multiply the 3 dimensions together. I like how I said it. 2x and 11 minus 2x. And that's our volume function. Somewhat complicated. Not obvious what minimizes that when I look at it. I have no idea, honestly, what the optimal answer is. But I do know a few things that if someone asked me to optimize this, I sure would like to use the process we just did. So we're gonna come up with some bounds for X. So X is gonna be between two numbers. Now I want you to think about this physically. What's the least I would cut out? What's the worst thing I could cut out? Like I lose my job. My job was one damn thing. I had one job, make a buck. Nothing. So I go to my boss and I say, here's your box. I used calculus and removed 0 from the corners. It's the sheet of paper you gave me. So if you remove nothing, you're still stuck with your piece of paper, but that's a possible thing. What is the most I can remove?
8.5.
How much?
8.5.
8.5. How'd you get? Well, if I cut the whole 8.5 out, that means this cut comes down here. Right, because I'm gonna cut it off both sides, so.
4.25.
4.25.
Yeah.
I could only cut it a maximum 4.25 out. Now look, we wanna use this side as our constraint as opposed to this. I don't wanna say 5.5 because that exceeds, if you cut 5.5 from both sides here, that's not possible. So I'm looking for the most restrictive thing, and I'm gonna make those my bounds. Let me stop, let me know if that sounds okay. So for all these word problems, you're gonna want to do a model, an equation model, and then a constraint. So this is our constraint. All right, let's do some calculus, but let's make life a little better first. Let's multiply this beast out. So I'll help you out here. So we're gonna find extrema of v of x equals. So if we multiply this out, man, oh man, I might need some help. So this is gonna be x. I'm gonna FOIL. Could someone do 8.5 times 11 for us, please? That times that.
93.5.
Thank you, 93.5, thank you, Leo. And then here I'm gonna get 22x, negative 22x, and then here I'm gonna get minus 17x, so that should be minus 39x. Let me know if that sounds right. 22 and 17, 22 and 17, yeah, I think that's good. And then plus 4x squared for the L, the last two terms. Still got that x out in front, so I'm gonna distribute that through, And our v of x is 93.5x minus 39x squared plus 4x cubed. This is probably not going to be pretty, because I made this problem up, and I don't know, the numbers are made up, so it's gonna be nasty. But that's good, because life is nasty, right? And life isn't like a math class where everything works out nice. Step one, your job, find the critical values in our interval. Here's the hard job, right? This is, besides setting it up, this is the second hardest job, I guess. You might need a calculator. You might need the quadratic formula. I got a feeling the quadratic formula is going to come in handy. To remind you of that. Oh, that's my garbage. Quadratic form. I'm definitely gonna need y'all to give me numbers. My phone is my calculator. Do you have numbers, Sophia?
Yeah, I just.
Oh, yeah, yeah.
Like, does it matter if you use, cause I used A instead of X.
Oh shit, yes, thank you. I totally did this dumbass. Thank you. Yes, Sophia, thanks. Thank you. I read this backwards like a doofus. That's A. What a knucklehead. Thanks, Sophia. That's C. Blah, blah, blah. So that's actually better. B, at least I got the B right. Didn't screw that up. And then still that. And then it's -4. I guess I didn't screw this up either, 'cause
It's just the.
yeah, no, you're right. It's really important though. It's a huge answer. Thank you. Does that look better?
Well, that's what I got for, well, that
For
was
what?
plus.
Cool. 4 point. Oh, the plus version. Yeah, I think the minus version will turn negative. Can we do both? Just to see. Yeah, okay, cool. So the first one, what was the plus version you got? Sorry to make you
That's
do.
okay, 4.91, but that's just.
Yes, exactly. But then that was when x was what? Oh, no, that was the solution, right. That's right, yes. 4.91 or
And then that
1.59.
1 point, thank you, thank you. Cool.
And then you wanna look for the critical values in the interval, right? So then we restrict ourselves to just one. Few, actually I can do the outer too.
Eddie, did you get a final volume for the 1.59? What'd you get?
Well, I just want to go for
Yeah, let's do 1.59. This is important. We're doing some serious work here.
66.
Thank you. Pretty damn close. Yes, sir. Did you get something
Would-
different or? Yeah.
No, would we describe the minimum as both of the values?
Yeah, great question. Yes, so sometimes your max or min can be achieved in multiple locations. So absolutely, Leo. So here we would say we have an absolute min of 0 at the endpoints at x equals 0 and x equals 4.25, because we don't even have a box in those cases. And then we have an absolute max of 66.14 at x equals 1.59. Sound good? Good, cool. That's kind of, I don't think we should do anything else today. I think you agree. I'm sure you agree. So, Wednesday, I'm gonna bring in some stuff. We're gonna do a work day, work some problems, and just kind of chill out and have math club. It's kind of like our little math club. I'm here to hang out and talk about any of this with you. Reminder, not this Friday, but the 30th, we do not have, our 31st, Halloween, we're not meeting, Friday the 31st. I like saying it because I like hearing it. Leo, would you get stop on that for me, sir?
Oh, yeah.
Thank you.